And also last presentation in this session is given by Gino Karotsov on NextWorks. The title of the presentation is Implementation of the FELIX SDN Experimental Facility.
Thank you. So for those of you who were in the tutorial this morning, this is sort of extra deep dive into the architecture, and since I guess the phases are more or less the same, I'll try to provide you with some further details much more related to the paper that we have published here. The aim of this in this session was not definitely to cover the wireless part, but to deal much more with the testing part. And what we report here are implementation experiences. So what you find in the software that we have been discussing this morning, the concepts, and this is somehow related to what we have been also hearing before from the Etsy guys. Just a bit of rationale behind this testing activity in all this realm of SDN and NFV activities all around. Definitely, I guess you are all familiar with the need for this experimentation at large scale. Everybody working on something has been requested by someone reviewing the work, how much it scales. And scalability is one of the main points. And making tests at large scale is one of the main constraints of lab infrastructures. Federating things, having network programmable for your experiments, having software-defined networking tools that enable this and the possibility to make all of this happen is definitely the way to go. And within the overall future internet research and experimentation realm and funding program of the European Commission, we also find this FELIX project, which is a collaboration between EU and Japan, starting from the idea to implement large-scale experimentation across these countries. And definitely, FELIX is part of this overall need for experimentation at large scale, part of this FIRE, and our special focus is on the SDN and bandwidth on demand for the interconnection of different domains in different places for providing, in order to provide to the users, to the experimenters in our case, what is a sort of, private virtual network implemented on demand with the specific requirements of the user. As shown this morning, there are some takeaways from this project, and those are basically a federated framework, so a reference architecture, which we'll have described largely in the tutorial this morning, but is basically relying on some key concepts. The federation of test beds, so the idea to put together resources from different owners in different places of the world, according to standardized approach for federating things, and standardized is to be meant here in brackets. We will go deep into this in a few minutes. We need to couple with different type of technologies, different type of hardwares in terms of switching, open flow switching and the like, but also different type of computing resources. We may need to interconnect these islands, and this has to be done autonomously and automatically and on demand possibly. This last bit, the on-demand interconnection, was something which was definitely out of the normal workflow of creating normal virtual networks in SDN till today. Another takeaway of this project is the software, the FELIX management stack. It is open source implementation available on GitHub, and it is what you can basically use to deploy your island according to the architecture that will be summarized in the next slides. And then there is the test bed, so a distributed experimental facility made of different islands in Europe, in Japan, participating to this effort and implementing, validating the reference architecture with experiments. Just a clarification, the FIRE context is for testing at large scale in general may have a couple of tracks of development. One track is the one focusing on developing tools for this federation for making the reservations. The other track is the track for delivering the infrastructure to the external users for their experiments. FELIX is part of the first track. So we were developing this, and the architecture and the validation and the use cases that we have been defining are basically aimed to validate this concept, to validate what we have been produced. The next step will be to try to understand how this facility can be contributed to the community, can be sustained over the long term in order to offer an experimental infrastructure for the researchers in general. And starting with the architectures and the pictures, actually, we have been working in this space, what we call the FELIX space, which is our reference architecture. We started from the identification of key concepts that were needed. We started around 2013, and at that time, the ETSI specifications, for example, were not available yet. The SDN was still a movement confusing the OpenFlow protocol and the activities around that and the initial controllers with the real, definition of an architecture. An ONF architecture wasn't available at that time. And we started defining roles of orchestrator of resources, roles of resource managers, and interactions between those entities and the physical resources. This to say that actually there are commonalities here between this reference picture of the architecture and what you have seen then elaborated by ONF, IATF, ETSI, NFV in the different standards that we have now available for the public. And the idea of this FELIX space is to implement the reservation of these resources, to have the tool and the mechanism and the overall workflow management that is able to implement a virtual network across different islands with federated resources. Once the virtual network is created, it is represented by a slice, so one piece of these resources that are just delivered to me, isolated by the others. And on top of this slice, I can play whatever SDN or NFV tool I want. Obviously, the role of the experimenter is dual here. It will interact with the FELIX space in order to implement the virtual network. So it's the automation of the procurement, if you want, of the virtual network. And then it will interact with the control layer, so the control user space, where all the different SDN controllers needs to be deployed. And our architecture is basically decomposed in these main functional modules. And the aim of the paper that we have been publishing here is a sort of an overview of the implementation experience of this. Part of this has been largely discussed this morning in the tutorial, but actually the concept is to follow and to put on top of the reference architecture for this kind of projects, which is the Slice Federation architecture from the Genie, so the SFA, to put an orchestration level coupled with monitoring system and AAA facilities in order to authenticate the users and to allow policy-based behaviors and access to the resources. And from the SFA reference, we inherit basically the concept of the resource manager, splitting this functionally in different type of technologies and realms of control. One is the transport network, so the transit network, if you want, which is the network between islands. The other one is the SDN RM, so the SDN network where the OpenFlow switches are run within the island, so where the different flow specs are installed. And the stitching entity is something that is quite new and is the bridging between this LAN and the transit network. And the computing resource manager is the one which handles all the creation and lifecycle management for the resources which are much more in the computing side, so VMs in particular and servers. there has been discussion from the beginning of the day about the applicability of the NFV architecture to different type of domains other than network. In the picture from the ETSI architecture, you have seen different type of resources, computing, storage, and network resources, physical resources, mapped into virtual resources. Actually, you know, this is somehow in line with this. We cannot claim that we were anticipating NFV. No, this is maybe too much, but actually we may say that actually we were not that far from them. And definitely we were covering mostly the part which goes now under the management and orchestration part, where we have an orchestrator and we have different infrastructure managers. This can be mapped into this concept of resource manager and RO. Back to the issue of the standardization. Actually, and this is very much related also to one of the discussions that we had at the end of the previous session, this is one of the big issues. How many standards are doing things in this realm? How many people are, how many organizations have a voice here? Actually, in this context of fire experimentation, the reference de facto standard is generally the SFA and the compliancy with the Genie APIs. And we follow this, because this is a way to let different testbeds interoperate. Because in this community, specifically, if I want to integrate my island with islands in the US, from researchers in the US, or in Brazil, or in Europe, and I'm mentioning basically collaborations that those projects are establishing, I need to comply with this de facto standard, which in the end of the day is more a concept of deploying things, which says that actually I need to deploy RMs per technology. I need to have an interface here which has to provide the same sort of primitive methods in order to reserve, start and provision resources, allocate and deallocate them. All is here, and all the rest is defined in something which goes under the name of resource specification, which is a file in XML where basically all the descriptions are done. The ones a bit more, you know, used to networking control from the previous waves of, you know, GMPLS or MPLS or even before may argue that actually this is not poor standards. This is much more, let's say, agreement, bilateral agreement between parties. Basically, in this community, more or less it works like this. But the concepts, the architecture is very much in line with the same, the capturing of the same need, the need for orchestrating things, the need for implementing technology-specific behaviors and configurations on physical hardware. I'll try to go into some summary key features of the different components and try to show you basically the schema of this. So how we handle these functions within the real software that you can find basically in the GitHub. So basically all the different resource orchestrators and resource managers follow or are built on top of a reference de facto other standard or piece of tool, which is the aggregate manager from our EICT colleagues, so EI-SOL. And the design follows the Genie's rights-based federation, as I said. It is agnostic, so basically you don't need to know the type of the model of the switch. You simply need to specify the elements which are declared in the AirSpec. And the most important thing, the innovative thing for our RO concept, which is quite new in the realm of the FIRE projects, is this concept of hierarchies of ROs. Which is very much in line also with the discussion that we had about the hierarchies of SDN and the hierarchies of NFV. So our concept of hierarchy in the RO, which starts from the same need for scalability and reliability of the system, has been deployed or implemented in a geographical way. So the first element, the bottom of the stack, if you want, is the domain RO, which is mapped with the facility, so your island. The second domain or the second level of hierarchy is the country. The third domain is the continent. So back to one of the comments that Diego was doing in the previous session, 2, 3 levels of hierarchies. We were starting in principle saying that the hierarchies are configurable and we can choose whatever we want. We thought initially that actually there was a facility, country, continent split, but as usual, as in every attempt of implementing hierarchies, we ended up with 2-level hierarchies, one for the islands and one for the continent. Because actually having too many layers in the end of the day, yes, it allows scalability, but on the other hand, it is complexity. So this is one of the lessons learned, confirmed also in this context. And definitely the role of the RM is simply to coordinate different, the role of the RO is to coordinate the actions of the different resource manager and to command, to set actions, specific actions according to the Israel-based federation architecture, so always following the Genie API behaviors from the generic user request to the specific RM. So just the computing parts for the computing RM, just the networking part for the SDN RM, and so on and so forth. Obviously, there is a tracking of resources. There are monitoring things integrated with the RO. I'd like just to point out how this is done in practice. So the type of software that we have been developing, and that actually is part of what you can find on the GitHub. So all the things that are described here are available as open source, as I said. This is the master root of the FELIX software. And you have also documentation for all of this, and you can download, contribute, as largely explained in the morning. In principle, the approach was to use the same API here at the northbound and here at the southbound. And the northbound API is Genie v3 API. The southbound API to any peers is also Genie v3 API. So with respect to the issue of implementing the hierarchy, this works fine because we have the same API, same primitives on the two sides. What changes is only the contents at the different levels. What we have at the northbound is a bit more high level. What we have at the southbound is specific per technology. And the overall design is made of core components which maintain the configuration, the inventory of resources, dispatch the different events and requests. And there is obviously some storage of this information into our resource DB, which is a MongoDB that we use in our implementation. And all the different communications, Genie v3 communications towards the different resource manager is handled by a plugin series, a plugin set, which corresponds to any sort of resource manager that we had to implement. Obviously, the northbound side is triggered by actions from a GUI, from a user portal. And for this, we used a couple of tools. Omni Client, which is the CLI style type of tool, and JFed, that is very famous in this realm. The one thing in this research area is basically to try to maximize reuse whatever is available also from other projects, other initiatives in the community. So for this reason, we imported things like the EAI soil, like the Omni, JFed, and the like. So here you are with the rationale behind the reusage of all of this. Another RM, computing RM. Going to the main characterization points, there's an issue. This is the mediator between the specific hypervisor I may have in an island and the rest of the FELIX management stack. And as such, we were federating resources, and we discovered, for example, that because of the origin of the different islands, in Europe it was much more common to have Zen as an hypervisor, whilst our Japanese colleagues were more inclined to use KVM. For this reason, and the architecture is flexible to this, we implemented two types of CRM, one for Xen and the other one for KVM, because the role of this resource manager is exactly to translate the generic request for computing resources coming from the Genie northbound API it has to the specific physical infrastructure that it has to command. And as such, basically, we need to implement different type of codes in it. As usual, standard APIs for it, northbound, which is Genie v2 and v3 compatible, aspects which are agreed across the different members of the FELIX at least, but they derive from previous agreements also in other FIRE projects. And these are the features I've been describing before. Let's focus a bit on the internals of this module. The internal is quite similar to the others. It follows a sort of reference framework on top of which all the different RMs have been developed, which is the aggregate manager. There is always a dispatcher of the messages, parser and policy engine in order to implement the checks that are needed in order to validate which resources could be accessed. There are monitoring modules and drivers, specific drivers. In this case, it is the Zen driver shown to the specific hypervisor. All the rest is sort of, framework code for implementing the XML RFC layer and so on and so forth. Again, in the presentation, you find also the links to the documentation of all of this. The software-defined networking RM. In the end of the day, we can simplify all the things and say this is a wrapper to the FlowVisor, which is well-known virtualization tool in order to implement virtual networks with OpenFlow switches. I like just to point out that actually, depending on this behavior, depending on this dependency, we were evolving the OFAM developed by the Ophelia project, and this element is the same type of resource manager, same translator of configuration from Genie to specific OpenFlow commands, and we support FlowVisor 0.8.7 and the 1.4 with OpenFlow version 1.0 in our testbed. These are the internals. As you can see, the pattern is always the same. There is always a monitoring, a dispatcher, and mechanisms to validate whatever is policy-like for the experiment. And then we have the driver to the specific element, the physical element implementing the things. The transit network is the brand new things developed in this FELIX. And definitely our starting point was to implement a mediation between the chain of resource orchestrators towards the RM concept, towards the CS and NSI connectivity service provider or aggregator. NSI is a standard mechanism developed by OGF to implement this, and it is work in progress by different communities, in particular Glyph with a project which is called AutoGoal. It is part of the GEANT initiatives for the R&D, and basically was contributed as a facility, as an asset in terms of standard code and also access to the services, access to the network by some of the partners of the project. We developed this, which follows the mechanism of the aggregate manager, and in the end of the day is simply basically a forwarder of requests from the FELIX layer to the NSI layer. It's a sort of client towards the NSI. Stitching element is another new thing developed in this project. It is the need to let the two realms, the SDN realm and the transit network, match together, because there are different workflows with different results in terms of VLAN, in terms of connectivity that needs to be stitched. Those are the features that have been basically described during the tutorial today. But basically, it is a mechanism that allows us to to pass from the SDN realm to the NSI connectivity service, and we are working also on extending the stitching entity in order to create automatically GRE tunnels on demand in order to bypass the transit network in case it doesn't work. And this is one of the cases, because actually in all these experiments, in all these infrastructures, whatever is in the realm of the organization participating to the federation is something that is doable. It is in the domain of the doable things, which means that people can put their hands on, try to solve things. Whatever is interfacing with the transit networks, in the end of the day, results in interfacing with NOCs from other parties, and this means human interaction with other humans, nothing that the software can solve automatically. And this was unfortunately discovered just the night before the review. This is the design of the ERM, basically same pattern. I won't go into much details on this. I would basically say quite briefly, since the time is flowing, that we have also a mechanism for AAA in this infrastructure, and this is based on a certificate-based AAA approach developed by EICT, in which we have different things and different functions that were needed to be implemented. So service registry, in order to register all the different services that could be provided to the users, authorities for validating either the members or the different roles that have been described in details this morning, or the slice, and other services for logging and the project itself. So the tenant concept in our case is a project. This is the internal, so you will find all the details in the paper. I'd like just to point out a couple of things on the user access and on the use cases, just to capture your last minutes of attention on where we use all of this. In terms of user access, we are based on the choice of the Genie approach and the Genie APIs, we are basically open to the GUI, which are now on fashion for all the federation and the federation infrastructures, and in particular JFED. So we can support this. So we are completing all the integrations for the missing parts, but mostly we support this. Obviously, we can command all of this via Omni client, so sort of CLI. And part of the system also supports something which is an inheritance from Ophelia, which is Expedient, which is a GUI tool with graphical representations. So this to say, the standardization or complying with de facto standardization in this realm may allow you to reuse software tools for parts which are not your core development, like JFED, like Expedient to some extent, like Omni client, and you simply need to use them as is, without the need to develop them from scratch. This is the infrastructure that I guess is now clear, quite clear how it is deployed. These links here are links which are not permanent links. Those are NSI adjacencies, so those could be created on demand. Part of them are across the NSI, part of them are across VPNs. I like just to focus on the use case that actually has been shown in the morning and can be further detailed if you want at the demo booth in the other room. Basically, the first one that we showed was a live use case just to demonstrate the need for this. And it was basically the concept of streaming video in 4K from Japan to Europe. And the goal was to try to get a clue about how the infrastructure could work, how the user, in this case a content distribution provider, could use the sandbox of this FELIX infrastructure in order to understand, for example, which sort of network capacity was possible for the service or was needed for the service. A sort of planning tool in the sandbox without paying anything. Similarly, which time of real-time monitoring system could be implemented in order to implement switches of the different paths across the network, and with sort of application or even a validation step of the application developed in order to, in the control, in the user space, in order to implement the SDN behavior, so moving traffic from one flow to the other. So this is basically one of the applications of an infrastructure like this. Details of the different things used, those are basically the things that are in the user space deployed there. And I like just to point out that we were using a RIO SDN controller for the flows that have been shown in the morning. And the application on top of RIO was this HQMon, which was an SDN application which was collecting data on the different streams and reacting upon specific violation of thresholds in terms of quality. So lost frames and the like. This is the job not of the infrastructure owner, this is the job of the application developer coupled with the SDN control. So this is full user space. How to use an infrastructure like this. What I was mentioning before, all of this works across different countries because this could be one of the use cases. I want to stream something from one end of the world to the other. Think about a sports event or software things like that. Doing things with these software tools is a kind of magic, so it works. And when the software is tuned and consolidated, you always get, services up and running. But the point is that even the single ping across the transit network in the data plane may fail. And the reason is that actually you need to coordinate all these bubbles here, which are different NOCs, different networks, where, for example, the software is responding positively to the request, is acknowledging your request, and you are happy because your workflow is completed, but in the end of the day, the data plane is not configured as expected. As such, there's still the human intervention I was mentioning before, and it's likely that intercontinental connections may result also in intercontinental EDACHs. We are working on other use cases, obviously, because the infrastructure is quite flexible to different scenarios. I'd like just to point out, to conclude, two kinds of experiments that we are now consolidating in this infrastructure, and we plan to produce results of this in the next months. The first one, or the first class, is this one that you see quite similar in terms of images. Those are what we call infrastructure use cases. So the idea of using this distributed infrastructure to test what a follow the sun, follow the moon principle may mean. And so the idea of moving workloads, virtual machines, from one island in one place in the world to other islands, according to policies to be developed in the application layer, so again, user space, across this virtual network, which is defined here. Someone may argue, okay, Google does this every day from a long time with the YouTube and the like. Perfect, indeed, this is the case. We are trying to allow the experimenter to test whatever new algorithm may be used for implementing this follow the sun, follow the moon. Another item which is very much related to the consortium we are is this disaster recovery by migrating infrastructure as a service to a remote DC. Think about what happened with the Fukushima event in Japan, and actually this is the FELIX project, which is a EU-Japan collaboration. At that time, they had full data centers interrupted, and the need was to migrate the full infrastructure as a service running in a data center to another data center on top of another infrastructure as a service, sort of hierarchy. Okay, so this is what we are trying to implement across the Japanese islands, actually. And the idea is to migrate the full stack here of the virtual infrastructure as a service systems to another data center using the infrastructure, and so the algorithms that can coordinate all of this. Another use case very much related to this is related to the mobility of users. Think about a traveling businessman or a traveling researcher who has a virtual machine running, say, in Tokyo, and he has to move, for example, to EWSDN and wants to continue working with this virtual machine, and, for example, with a mechanism similar to EDUROAM, may want to allocate his virtual machine into the PSNC island, which is part of the federation. Those are infrastructure use cases because actually rely on this infrastructure. The final one I would like to describe to you, which is work in progress exactly in these days, is the idea of using an infrastructure like this in order to deploy a sensing of data and acquisition of data in one point of the world and deliver the data to another side of the world. Which could be the application of this? Think about satellite data. Those are generally captured by antennas in given parts of the globe, typically next to the North Pole. And one of the issues for the space agencies working together, for example, the European Space Agency with the Japanese Space Agency, is that the acquisition of data from European satellites occurs in Europe, but needs to be consumed, data, images needs to be consumed by the Japanese colleagues, more or less in near real time. And the issue with the best effort internet with normal FTP transfers of these images across the normal internet, the best effort internet, is that it takes too much, it takes long. And with this in between, we are able to guarantee pipes, we are able to implement a mechanism of chaining of different functions for the pre-processing of the images and the transfer of compacted images, which is a small amount of data moving across the long distance. So these are the features that this infrastructure can deploy. Plus the next one, the one that you can possibly bring in if you are interested in working with us or on top of this infrastructure. In summary, FELIX is an infrastructure in the end, plus tools and software that facilitate the federation and integration of different network and computing resources. Different owners, different islands, all federated under a single orchestrating entity. It is, in the end of the day, a generalized control framework, which has a lot of commonalities with the design patterns, architectural patterns of the SDN controllers or the SDN architecture and the NFV, mostly for what concerns the orchestration and the management of resources. It is definitely recursive, and this recursion is by design, and it is open source software. We are now running the use cases in order to demonstrate that actually it works in this specific realm. And our goal is to deliver the full set of architecture specification, the software, and our lesson learned, the ones that part of them have been provided today in this talk, to the community, to the FIRE community in particular, in order to, let's say, progress in the evolution of this. That's it.
Thank you very much for this very interesting presentation.